Welcome back, class, to lecture 9, in which we're going to move away from just talking about matrices in general and start solving those sets of simultaneous linear equations by hand. So as a reminder, last time you should have, we covered a review of matrices, talked about converting linear equations into matrix notation, and solving linear equations using those built-in MATLAB functions. Today we're going to move away from that and start talking about solving those functions by hand and sort of what MATLAB is doing behind the scenes. Particularly using graphical methods, Cramer's rule, forward elimination and back substitution, also known as Gaussian elimination. Then we'll talk a little bit about conditioning of matrices, how we can use partial pivoting to make sure our matrices are well conditioned, and then finally talking about tridiagonal systems, which are highly efficient for solving simultaneous linear equations. First, I want to talk about a graphical method to use when we're solving these equations. So when we go to solve linear equations, what we're really essentially saying is we're looking for the point where two lines converge. So let's say, for example, we have this 3x1 plus 2x2 equals 18, and we want to find where that where x1 and x2 also solve the equation negative x1 plus 2x2 equals 2. What we're really looking for is where these two functions cross. Right? And so if we have a small set of equations, we can sort of, namely two equations, we can see graphically what's happening. In this case, we can tell that we have a very distinct point where these two are going to cross. They're moving in very different directions, and we have a single point where they're going to cross. It will be, it should be relatively easy to find where they intersect each other. This is not only always the case. There are several other cases where there may be a difficult to find solution or no solution at all. Let's take, for example, this first graph. Here we have negative 1/2 x1 plus x2 equals 1. And on the face of it, it may look like that's different than negative 1/2 x1 plus x2 equals 1/2. But if we graph these out, we'll see that there's no crossing point, right? This top line here and the bottom line here are never going to cross. So there's no actual solution to that equation. On the other hand, we can have cases where an infinite number of solutions exist. This is shown here with a similar equation. If we have negative 1/2 x1 plus x2 equals 1 and negative x1 plus 2x2 equals 2, if we plot these, you'll see that they fall into the same line, right? I can convert this top equation into the bottom by multiplying by 2. I would get negative x1 plus 2x2 equals 2, right? So they're the same equation. There's an infinite set of solutions. And the third sort of case that's not great for solving simultaneous equations is where the system is ill-conditioned. So in this case, we have two lines shown here and shown here that are almost on top of each other. So the difference between these two values at any point is very small. This means it's going to be difficult for us to mathematically distinguish one line from the other. So this is called an ill-conditioned system. And we're going to get to how we deal with that in a little bit, but I just want to set that stage of where we're going to go. Before we handle those cases that are difficult or impossible to solve, though, I want to talk about cases like we saw in the previous slide where they're very easy to solve. And the first way to do this is using determinants. So remember, the determinant of a matrix is going to be written like this, where we have D, and then we have this sort of absolute value around A. Let's look at the simplest matrix of a 1-by-1 matrix. In this case, we could say that our matrix formed A11 is equal to just a 1, 1. So maybe we'll put in D of that matrix is just going to be that one single element. So this is not very interesting. Let's take a look at 2 cross 2. In this case, the determinant of a matrix, say A11, A12, A21, A22, is going to be the products along this crossed axis. So A11 times A22 minus what's happening on the other cross axes. So A12 times A21. All right. So things are going to get a little bit more complicated. Things are going to get a little bit more complicated when I move into, say, a 3-dimensional matrix where I have 3 cross 3. Maybe say D is equal to A11, A12, A13, A21, A22, A23, then A31, A32, A33. And in this case, I'm going to go through, I'm going to identify the first element in the A11 slot, A11, and multiply that by the determinant of the resulting matrix. So A22, A23, A32, A33. And we can go in and solve this 2-dimensional matrix determinant using the information above. But we're going to just keep plowing ahead. We can then do our next step. So we're going to subtract off A 1, 2. And then we're going to take the determinant of the other, of the remaining elements. So I'm going to cross out the row that A is in. I'm going to take the determinant of the resulting leftover pieces. So that's A21, A23, A31, A33. And we can do that with the final piece, A33. Maybe erase the green lines. Pick a different color. We'll take this A13, so we cross out those 2 lines, and we then take the determinant of the remaining 4 elements. A21, A22, A31, A32. All right, so we can build up these determinants by taking sort of these cross multiplication products. As we move up to higher dimensionalities, we need to start identifying, taking summations of determinants of lower order to make sure that we have all of the elements included. I'm going to comment here that we can already see that when we're getting towards a size 3 by 3, we're starting to get to a relatively complex math, and we're going to get even more complicated if we go to matrices larger than 3 by 3. So therefore, in this class, we're only going to stick by 3 by 3 matrices, and so we're only going to determinants for solving linear algebra problems. So because they're going to get too complicated, so we're going to just stick with this formula. However, the same concepts are going to apply to higher order formulas, and that's what computer programs will do behind the scenes. Now that we know a little bit about determinants, we're going to use them in order to solve solve linear algebra problems. The method of using determinants to solve these matrix math problems is called Cramer's rule. So Cramer's rule says that each unknown of a system of linear algebraic equations may be expressed as a function of two determinants with the denominator d and the numerator obtained from d by replacing one of the columns of the coefficients of the unknown in the question by the constraints b1, b2, all the way to bn. So that's sort of our technical definition, but let's see what that actually means. So let's take a matrix, say matrix A. We have our vector x and our vector b. And what Cramer's rule states is we're going to need to take a ratio of two determinants. The first determinant being some number d1, that's going to be the determinant where we're going to replace a column with the b's, and then a second determinant, just regular d, that's going to be based off of this matrix A. Okay. So we can put this into place. So here we have the equation for our determinant d. So this is what's going to come down and sit as the denominator. Here, once again, notice that I have the determinant symbol as just those up and down vertical lines. And then within that determinant are just all the elements from matrix A. For B, we're going to take, for D1, we're going to take the determinant D, write it out again, but replace this first row, this first column with the vector B. How we know that this is D1 is because it's got that one there, it's replacing that first column, and this is going to go at the top. And once again, it's for unknown 1. And I can write this out again. Maybe for D2, I take that general D determinant, and this time I replace this second column with B1, B2, B3. Noting again that it's the second column for D2, and it gives us X2. And then, not to get overly redundant, but we can do this again for finding X3. This time we're going to replace column 3. So these A's are going to be replaced by these B's. We can write out determinant 3, the first column of A's, the second column of A's, and then those column of B's. And that will then give us the X3. Let's put this in practice and see how we can do this out. So the first thing that we need is a series of linear equations. So I've written out 3 linear equations. The first one being 0.3x1 plus 0.52x2 plus x3 equals negative 0.01. Then we have 0.5x1 plus x2 plus 1.9x3 equals 0.67. And then finally 0.1x1 plus 0.3x2 plus 0.5x3 equals negative 0.44. So as a first step, we should go in and turn this into a series of matrix equations. So we should get used to this by now. So we have 0.3, 0.52, 1, 0.5, dragging this 0.5 down, then 1, 1.9, 0.1, 0.3, 0.5. That's going to make that matrix A. We have x1, x2, x3, and then that's going to equal negative 0.01, 0.67, and negative 0.44. Right. So we've got this in matrix form. Now we're ready to solve out the system equations. In this case, we're asked to find x2. So we're going to need to do 3 steps. One, we're going to need to find that base D determinant. Then we're going to find the D2 determinant because we're interested in x2. And then finally, we're going to divide D2 by the generic D term. So let's start this out. So remember, D is our determinant here. So 0.3, 0.52, and 1, 0.5, 1, 1.9, 0.1, 0.3, and 0.5. We're ready to take the determinant. Using that formula that we had on the previous a few slides ago, we're going to take that element that's in A11, put that out front, 0.3, and multiply that by the determinant of what's sitting in this lower right-hand corner. So the determinant of 1, 1.9, 0.3, 0.5. We're going to subtract off what's in that first row second column, so 0.52 times the determinant of 0.5, 1.9, 0.1, 0.5, and then add in our last element. We take that upper right-hand corner, number 1, multiply it by the determinant of the elements in the lower left-hand corner, so 0.5, 1, 0.1, 0.3. All right. And all of this, when I do this out, I'm going to put it here maybe in a different color, is equal to negative 0.0022. All right, so we have D. Now we're ready to move on to find determinant 2. In this case, right, we're looking for the second piece. So we maintain the first column, 0.3, 0.5, 0.1. We replace the second column with that B vector, which we have over on this screen. So negative 0.01, 0.67, negative 0.44. And then we can solve out, we bring down that third vector, that third column of our matrix over here. So we have 1, 1.9, and 0.5. We're ready to solve this out again. We're going to take that same approach. We take the A11 case, so 0.3 times the determinant of the remaining pieces, which is 0.67, 1.9, negative 0.44, 0.5, minus minus that element in that first set. So we need to subtract this off. So because this is a negative 1 here, we take a negative of a negative 1. A negative of that negative 0.01. This gives us 0.5. When I take the remaining numbers from the determinant, and I'm ready for that last element, which is just a plain old 1 times what's in the lower corner, 0.5, 0.67, 0.1, and negative 0.44. When I do this all out, I end up getting 0.0649. Now we have D1, we have D2. We're ready to do that third step, which is divide. So this is right, the easy step. We have x2 is d2 over d. This is our negative, oops. This is that d2, so 0.0649 all over negative 0.0022. Sit here, we can get out our calculators and do the math. This ends up being 29.5. So in essence, we now have a method to solve out the x2's in this equation using Cramer's rule. We can do the same thing for the other two solutions. Here's x1. What you'll notice is that first column of the determinant, right, are those b vectors, while the second row of the determinant is from that equation, right? So from that matrix, and then same thing with that third row, they're coming from this that farthest right-hand column of the matrix. When you do out the determinant, which I'm not going to do for time constraints, you should get 0.03278, which gives an x1 value of negative 14.9. And then we can do the same thing with x3. Once again, noticing that that third column in that D3 matrix are the value from the right-hand side of that equation. Right? So we've gone through, we've completed Cramer's rule for x1, x2, x3, and we've solved out that series of simultaneous equations by hand. As I've mentioned before when we were talking about determinants, solving out determinants for larger than, say, 3 values can become for a 3 by 3 matrix can become quite challenging. So instead, we want to do a different type of operation so that we can tackle much larger matrices that may come across in chemical engineering problems. The method that we're going to do this is called Gaussian elimination, right? So think back to when you were first learning to do solving simultaneous equations, right? You had maybe say ax1 plus bx2 equaled c, and then you had maybe dx1 plus ex2 equaled f. If you remember, right, we solved for first x1 in terms of x2, and then we would take this value and plug it into the first equation to solve for x2, and then we could back solve into the second equation. Forward elimination and Gaussian elimination, which is forward elimination and the back substitution, is going to work essentially the same way, but we're going to do it using matrices, which should hopefully make things a little bit easier to keep track of. So forward elimination is going to be our first step of naive Gaussian elimination. The idea is we want to take our matrices, so here's say that A matrix that we've been working with, and here's that B vector, and we've written it as this simple notation where that dashed line is essentially going to be that x equals sign, just to give us a little bit easier time writing it. And the idea is going to be, let's manipulate this matrix so that we can form this upper triangular matrix. The idea being, remembering that there's zeros here, is once we have it on this upper triangular matrix, I'm able to solve for, say, x3. Then I'll be able to use that x3 value to solve for that second row. Then I'll be able to use that x3 and x2 to solve for x1. Okay, so in order to move from the top matrix, in order to do this conversion, what we're going to need to do is we're going to need to find we need to find what we can multiply row 1 by. So find a multiplicative factor. We're going to multiply the first row by it. And then subtract it, subtract the result from, say, the second row, third row, etc. Right? And so we're going to do this one after again and again until we get that nice upper triangular matrix. Now, I personally think the easiest way to sort of see how to do this is by an example. So let's go in and take an example shown here. Once again, I've got three equations with 3 unknowns. The first thing that we're going to want to do is convert this out of, convert this from being a sort of set of 3 equations into a matrix form. So let's do that right now. So we have 3, I'm going to just take all those first variables, 3, negative 0.1, negative 0.2. That second row of the matrix is 0.1, 7, negative 0.3. And then the third row is 0.3, negative 0.2, 10. I'm going to put that dashed line to sort of represent the x vector, and then I can write out my 3 elements of my b vector. Right? So this is the matrix that we want to operate on. So let's go in and see how we're going to do this. So once again, I can write out very briefly that matrix that we're going to want to operate on. Okay, so let's take, let's work on the first 2 rows. So remember, I want to take this and make something that looks like this. So 3, negative 0.1. That looks like this: 1, 1, A, 1, 2, A, 1, 3, A, 2, 2, A, 2, 3, A, 3, 3, B1, B2, B3, right? This is the form that we need to put it in. So we don't need to do anything to that top column. It's already in the form that we want. We do need to do something with that second, sorry, we don't need to do anything with the top row. It's already in this form. It's got 3 values across the top. We're good to go. We do need to do something with that second row, right? We need to get rid of this 0.1, right? So we have to get rid of this piece. So we need to find a way to do this. So we're going to subtract something about that first column from that third column in order to transform it into this form. So let's just write out what that first equation set might look like. So 0.3, 3, negative 0.1, negative 0.2, and 7.85. All right, so we want to multiply it by something, so x times all of this, such that x times 3 is equal to this first value, right? So equal to 0.1. Why we want to do this is because we can multiply this out. So this would be x equals 0.0333, because now if I multiply that top row by that value, so 0.0333 times 3, negative 0.1, negative 0.2, 8.85. When I multiply all these out, I get 0.01, 0.1, negative 0.0033, negative 0.00666, repeating, and then 0.261. Why this is important is now, if I look at that second row of my matrix, maybe go back to purple, I have 0.17, negative 0.3, negative 19.3. So now I can subtract one from the other, and it will eliminate that first variable, right? So essentially, I'm just taking those two equations, subtracting one from the other. So I'm going to take that top case and subtract the top from the bottom. I get 7.000033, negative 0.2933, and then negative 19.56. All right, so all this math is essentially going to has enabled me, by subtracting the top equation from the bottom equation multiplied out, I'm going to be able to rearrange that second row. So let me go in. I'm going to erase those values in that matrix. I'm going to put in these new values. So now I have a 0 here, 7.0003, negative 0.2933, and negative 19.56. So I've now replaced that second row with the subtracted value between the first row and the second row. Right? Good. So now if I compare what I have to what I want, so if I compare this top matrix in purple to the bottom matrix, we can see that I'm much closer to my desired value. All right, I have the first two rows which have the appropriate form of having, the first row has no zeros in the first column. The second row has 1 0 in the first column. So I'm almost there. The issue, of course, being now that third row. So I need to do something to get that third row into shape. We're going to use the same procedure as before, right? We need to get rid of, this time, we need to get rid of this 3. So let's put it into a little bit more, say, mathematical terms. So we're going to take the value in this column, the value at that bottom row first column, over the value in the first row first column, so 3. I'm going to multiply that through that entire top row, so 3, negative 0.1, negative 0.2, 7.85. And this then is going to give me what I'm going to subtract off. I picked this top multiplication, this 0.3 over 3 divisor, so that I'm ensured that when I multiply it through, I get back that 0.3. Right? So let's do that multiplication through. If I do that, we have 0.3, negative 0.01, negative 0.02, and 0.785. Just multiplying that value through. Now I can line up my bottom case. That I can write out my bottom row. Which I somehow, there we go, 10 and 71.4. So now I can take one, subtract it off from the other. I end up with 0, negative 1, oops, I end up with 0, 0.19. Remember, I need to multiply the entire thing through by 0. Negative 10.02 and negative 70.615, right? So just multiplied through by negative 1 and added the 2 together. This new row is going to replace the old row. Right? So I'm going to go ahead and do that. I'm going to take out these series of numbers. And we're going to replace this row, 0, 0.19, negative 10.02, and negative 70.615. I haven't changed the values, I'm just multiplying and then adding and subtracting. You'll see, now that I have this, that I'm getting quite close. I have the first row, a set of numbers, so that first row is good to go. If I look at my second row, I have in this column, in that second row, I've got a 0 in the first column and numbers everywhere. But in the third column, I only have a 0 in the first column. I still have an issue. Because I don't have a 0 in that second column. So I need to do something with my, to the system in order to get rid of that 0.19. So let's think about what we can do for a second. I can't use row 1, right? Before I subtracted row 1 from row 3. But if I do anything with row 1, I'm going to end up changing that 0 in that first column, which I don't want to do. I like that 0 being there. So I have to work with this second row, which already has a 0 out front. So if I do any subtraction or multiplication through, I'm going to maintain that first column 0. So let me clean the screen up a little bit, and then we'll go in and we'll do this math steps again. Once again, we're going to start by, I guess maybe I'll switch to red. We're going to start by writing out that second column. That's what we're going to subtract off, or that's what we're going to modify things by. So you have the 7.0003, negative 0.2933, and negative 19.56. So we need to multiply this whole row by some number so that when I subtract off, I end up having that negative 0.19 in the second column. So I can do this by taking 0.19 over that 7.0003, so that when I multiply this through, that entry will become 0.19. Okay, so let's go ahead and do that. When I multiply this through, 0 times 0.19 over 7.003 is 0. That second entry is 0.19, right? Because it's 0.19 times 7.003 over 7.003. Those sevens cancel out. So I'm left with 0.19. This is perfect. This is exactly what I'm looking for. We can then do that third step. This gives us negative 0.0079. And then we can finally do that for that 19, which gives us negative 0.53. All right, so that's our multiplication step. I'm now going to take that third row, write it down here, so we can do that math relatively easily. And now I'm just going to multiply through by negative 1, and I can then add them together to get that new row column. So that's 0, 0 minus 0, negative 0.19 minus 0.19, once again 0. Add these together, I get 10.012, and then finally for that last column, I have 70.84. All right, now I'm good to go. I can take that end result and swap it out for that third column. So let me erase those entries. We have 0, 0, 10.012, and 70.84. Now let's look and see how we're doing. That first row is always good to go. The second row has a 0 in the first column. It's good. The third row has 2 zeros in the first 2 columns. It's good to go. Right? So we now have a matrix that looks like our desired matrix, and we've completed forward elimination. However, forward elimination isn't enough. We need to now do back substitution in order to figure out what x1, 2, and 3 are. So back substitution, we start by taking the last row. Right? And we can remember that this dotted line is standing for these different x's, right? So here we have 0, 0. So once again, my x3 value is what's on the right divided by what's on the left, right? So remembering, if I were to multiply this out, I have 0x1 plus 0x2 plus a33 prime prime x3 must equal b3 prime prime. Well, x3 must be b3 prime prime over a33 prime prime. Right? So once we have that x3 value, I'm going to take that x3 and use that in solving for that second equation. We can write this out again, 0x1 plus a22 prime plus a33 double prime x3. Oops, sorry. A23 prime x3 equals b2 prime. Well, this is 0. We're interested in solving for what x2 is, and a23 prime x3, this is just a number, right? Because we've already solved out for what x3 is, so it's not a variable anymore. So we have a number, we have only one variable, we can rearrange and get x2, and then we can do the same thing for x1 using both x2 and x3 in that top line equation. Let's go ahead and put this into practice. So here we have that matrix that we have that we got from forward elimination, and so now we're ready for our back substitution. So we can use the equation. We can either write this out. So I'll write it out the first time. 10.012 times x3 equals 70.08. This then tells us that x3 is equal to 7. Or we can use the equation from the previous slide, which just says x3 is equal to b3 double prime over a33 double prime. I can pull that b3 double prime, so 70.08 over 10.012. That's still going to be 7. So you can either write out the equations if you want, or just use the equations from the previous slide. So we can keep track of this. I'm going to put my x vector down here. We now have x3 is 7. And now we can do this for x2. X2 is equal to b2 prime minus a23 prime x3 over a22 prime. I can pull the numbers. I have negative 19.56 minus a23 is negative 0.2933 times x3, which is 7, all over a22 double prime. So that's our 7.0033. I do all of this out, and we get x2 x2 is negative 2.5. So we can punch that into our vector, negative 2.5. We're ready to do x3, right? x3, we can either write out the whole equation based on that top row, or we can use the equation. So that's b1 minus a13 x2 minus a12 x2 minus a13 x3. Those numbers have to match. all over A11. We can punch in our numbers. B1 is, of course, 7.85 minus negative 0.1 x2 times minus A3 is negative 0.2 times x3, which is 7, all over A11, which is 3. If I do all of this out, we find that x1 is equal to 3. So I can plug that into my variable. Good, so it looks like we've now solved our equation, right? I have my x vector. But like any good math students, we should take that x, plug it back in, and make sure that we're getting what we expect to be getting. So let's do this out. So we had 3 times x1, which was 3, minus 0.1 times x2, minus 0.2 times x3, which we had set to be 7. And if I do all of this out, it ends up being 7.85. If you remember, this is exactly equal to what that equation said. We can do the same thing for the second equation, which is 0.1 times 3 plus 7 times negative 2.5 minus 0.3 times 7. This ends up multiplied all out, we get negative 19.3. And lo and behold, that is what those previous equations that we were searching for. That was B2. So check, check. And then for the final check, we had 0.3 x1 minus 0.2 times x2 plus 10 times x3. You multiply all of this out, we end up with 71.4, which is exactly what we were looking for, 71.4. So that gets a check mark. So always make sure that we're checking our results. It looks like our x vector is truly 3, negative 2.5, and 7. Let's talk about how efficient this is. So remember, we have two steps that we're taking, forward elimination and back substitution. We can count before we even start how many different operations we're going to need to do in order to carry out this system, or these sets of of operations. Right? Without sort of thinking about it, we went through all those different math operations. We can do that with either integers, or more likely, as seen on the previous slides, with decimals. In computer science terms, those decimals are known as floating points. And when I do mathematical operations with floating points, these are called floating point operations, or flops. So if you go out to buy a computer, or you look on the websites for the world's fastest computer, they'll report how many flops they can do. So floating operations per second. So you or I probably can do maybe one floating point operation per second, but your desktop or laptop, whatever you're working on, is going to be doing millions or billions of flops per second. And so when we look at what the forward elimination can do, it requires on the order of 2 times the number of rows or columns cubed over 3 flops to do forward elimination. Back substitution requires an order of n squared flops. So the total number of flops that we need are roughly 2 times n cubed over 3. Really what I'm trying to say is that as systems get larger, the time required to solve them, or the time required to solve a matrix, is roughly cubes, is a cubic function of the size of that matrix, right? So we spend a lot of time in doing forward elimination, and we have rapidly scaling behavior. I now want to switch from talking about how to do Gaussian elimination to some problems that we may have doing it, and how we can use pivoting to solve those problems. The major problem that we're going to have in solving out matrices using Gaussian elimination is if we have a 0 on the diagonal. So remember, we've structured our problem such that we end up with, say, variables in the upper triangle and elements that are sitting in the upper triangle and zeros in that lower triangle. Right? So if I have this matrix and A22 happens to be approximately 0, or let's actually just say is equal to 0, when I go to solve out that second row, I'm going to have an equation that says 0x1 plus 0x2 plus A23x3 equals some number, right? And that second equation, that second row, is supposed to give me information about x2, but it's multiplied by 0. I'm not going to get the x2 information that I need. If I'm close to 0, so that's if I'm 0, I've got that immediate and obvious problem, right? If I'm close to 0, I'm still going to have this problem because when I go to do that, x2 equals b2 minus a23 x3 over a22, right? If this is very small, this is going to blow up and be huge. And small differences in this number with how many decimal points I'm keeping track of is going to change the behavior. So one way that we're going to get around this issue is to swap different rows in the matrix. We want to swap these so that the largest element in the remaining rows is in that first column, right? So that this is the largest value, here's the largest value, and here's the largest value. So we want to make sure that we have big values along the diagonal so that I can make sure that I don't have this blow up area. Right? And so this is called pivoting or partial pivoting. Let's see how this is going to work. Here we once again have two equations with two unknowns. The first equation has this number 0.0003 before x1. It's very close to 0. We're going to see what happens if I don't pivot, and then we'll see how we can fix this when I do. So let's go ahead and take that matrix and start doing our math. So the first step that I need to do is multiply that top row by 1 over 0.0003, so that when I do the subtraction, I get 0.001. When I do this multiplication out, I get 1 plus 10,000 x2 equals 6,667. So this is just taking that and multiplying through. When I subtract if I take this top row, subtract it off, I get that 0x1, and then I'm taking 10,000 minus 1. So that's negative 9,999x2, and then at negative 666. Right? So this is that end result of my forward substitution, forward elimination. Now I'm ready for back substitution. So I'm going to divide 6,666 by negative 9,966, and we'll get x equals 2/3. Okay, this isn't so much a problem. But what happens when I back substitute in to that first equation? So when I back substitute in up here, I have x1 equals 2.0001 minus negative 3 times 2/3 over 0.0003. This number is very small. And this number is irrational, right? I can't tell a computer 2/3. I need to put in some sort of decimal form. Let's see what's going to happen. Here I've written out those two equations again. X2 is 2/3. X1 is 2.0001 minus 3 times 2/3 over 0.003. Okay. We have to tell the computer how many significant figures are we going to represent x2 by. So let's say we're relatively lazy, so we tell the computer you only need 3 significant figures. So we're going to represent x 2/3 by 0.667. Well, I can now take this number, which is an actual number, and plug it in up here. When I plug it in up here, I get x1 of being negative 3.33. As you'll see in a second, this represents a 1,000% error, right? We can check our answer once again by going to a more appropriate answer. Let's add just one more 6 into that figure, right? So we'll go to 6 significant figures. Now, when I plug that number in, I essentially have 0. Everything is going to cancel out. I have 100% error for my solution. Better, but not right. Okay, so let's go in, add in a 5th digit. Now when I add in the 5th digit, I can take x1 equals 2.0001 minus 3 times 0.66667 over 0.003. And now I have a number that's going to start looking like a number. We have 0.3. I can add in that 6th significant figure and that 7th significant figure, and we can start seeing those 3s populate through. So, but we're going to need many, many significant figures to keep track of, and we're still, so in this case, we have to represent it by 7 figures, and we're still not sure that we're totally converged. In the end, it is going to be 10% error, but we do need those 6 figures to make sure that we're there. Now let's see what happens if we pivot. So once again, we have these 2 equations written out, but we'll notice that the first line, the first column of the second row is bigger than the first column of the first row. So what I'm going to do is I'm going to take that and I'm going to stick that equation up top. Right? So I'm just going to take that and put it in this version. All I've done is I've swapped rows 1 and 2. By doing so, we have the largest number up front. The biggest A11 the biggest variable in the first column is in that first row. So now let's go ahead, redo that exercise maybe a little bit faster and see where we end up. So if I multiply through, sorry about my animations, I can take that first row. I'm going to multiply through by A21 over A11. So A 21 over A11, that's going to be, in this case, 0.0003. When I multiply through and do all the forward elimination, I end up with this equation. I now have 0 times x1 plus, 1 times x1 plus 1 times x2 equals 1, and 2.99997 times x2 equals 1.99998. I can go through, I still end up with x2 being equal to 2/3. But when I go and I back substitute into that top equation, I end up with x1 equals 1 minus 2/3 over 1. What you'll see is that number in the denominator is now no longer super close to 0. So it's not going to have this large inflating effect. So I can go and do the same exercise. Let's take 3 significant figures. So I'm going to say x2 is 2/3, but I'm only going to represent it by 3 significant figures. That's 0.667. When I punch that into that x1 equation, I end up with 0.333. In that first use, only 3 significant figures. My relative error is only 0.1%. That took 7 significant figures without pivoting to represent that same quality, right? If you remember back a few slides. By the time, and I can do this with more and more significant figures, by the time I hit 7, I essentially have, my error is in the order of 100,000th of a percent. Right? So merely by switching the ordering by pivoting, I can get a much more accurate answer. The last thing that I want to say about pivoting is that this is only a partial pivot, right? We only looked at that first row. This wasn't such a big problem, right? Because we had only a 2x2 setup. For full pivoting, if I had, say, a larger 3x3 matrix or three equations, 3 unknowns, I would need to go through and do make sure that that after I solved out for each column, I make sure that I repivot again so that I have that nice diagonal of really big numbers on that diagonal. The last topic that I'd like to talk to you about today is tridiagonal systems. So a tridiagonal system is a banded matrix. If you remember, banded matrices are these matrices that have these bands and then zeros on either side of the band. It's called a tridiagonal system because in this case, the band has width 3. So we have 3 elements in a row that are not 0, and then everything to the left is 0, and everything to the right is 0. So this tridiagonal system is going to be special because it's going to be it's going to be solved in the same way that we did Gaussian elimination, but it's much easier because we already have a lot of that work done for us because we already have a lot of zeros in our matrix. So where this is going to come in is the fact that we can get rid of the first element in each row without having to worry about the G's, the last element. So I can start altering, I can get rid of E2. I don't have to change G2 because that first row is 0. So anything that I subtract off is going to be multiplied by 0. It's not going to change G2. Same thing. E2, I'm looking to get rid of it. I know even before I start that whatever's in that set E2, that variable E2 is going to become a 0. So I really only need to worry about the diagonal element. I only need to worry about that diagonal element and then whatever the effects of that diagonal element are on what's happening on that right side of the equation. Right? So remembering back to Gaussian elimination, we can say that any of those diagonal elements is going to be what was there originally minus E over F minus 1. So say, right, this goes back to where we were multiplying that top through by E2 over F1 so that we can eliminate the E. Right? So that's sort of that E2 minus F1, right? That's that number that was getting multiplied through times G1 times G, which is that element that's in the same column as the F we're interested in. Okay? So relatively straightforward. This, in this case, each of these subscripts is referring to which row we're on. And then we can write the same sort of equation for what's happening on the right side of our equation. We have any Ri is going to be replaced by Ri minus Ei over f of I minus 1 times Ri minus 1. What you can see is it only takes, for each row, I only need to do 2 operations. So much faster, much easier than having to do repeated cycling for each row and column. Let's put tridiagonal matrix Gaussian elimination into some sort of practice. So let's do this case study here that we'll see if you're in heat transfer, you probably see something like this, and if you aren't in heat transfer, that you'll see in next year. Let's take a model of a rod shown. Here's this silver piece that is between 2 heated surfaces that are at different temperatures. So we have this T0 and this T5, one that's at 40 degrees and then one that's at 200 degrees. Many times in engineering, we want to know how hot or what the temperature distribution is through that rod. As you may recall, if you're in heat transfer, as you may recall, we can write out the equation for heat transfer as the second derivative of temperature with respect to x plus the heat transfer coefficient h prime is equal to the HA times T ambient minus T to account for convective heat transfer along the rod. And then subject to the boundary conditions, T naught equals 40 degrees and T at the other side equals 5 degrees. I don't want to get too into the weeds into heat transfer or solving differential equations because we're going to spend quite a lot of time on that in a second. But let me cut to the chase and say that we can model this heat transfer using this equation, where we have the temperature at any point along that rod can be solved for if we have Ti plus 1 minus Ti plus Ti minus 1 over the distance, that distance x squared, plus our heat transfer coefficient times the ambient minus Ti equals 0. In this case, this delta x is the spacing along the rod, how often we want to know the exact temperature. So I can, in this example, let's say that we have a certain value for h prime given in the problem as h prime equals 0.01. Let's say T ambient is equal to 20. And let's say we want to look at this section every 2 meters. So delta x is going to be 2 meters. I can take these coefficients or these constants, plug them into that top equation, and rearrange to isolate all the constants on the right, in this case 0.8 for the interior points, and all of the other ti's and all the different t's on the left, to put this into this variable type form. Now, as long as I'm at interior points, this equation will hold. So I can write this out for an equation looking at T1, or at x1, so that first point, second point, third point, and fourth point. Right? So we have all of these points set in there. Remembering, of course, that T0 was equal to 40 degrees and T5 was equal to 200 degrees from that boundary conditions. Once again, don't get tripped up on how we want to apply the differential equations. We'll get to that in a few chapters. So I can take these equations, once again, setting this to be 40 and this to be 200, and I can put them in matrix form. This is a constant, so I'm going to move it over onto this right-hand side. So when I put it in matrix form, I have a negative 40.8 on the right. I can do the same thing down here for this last case. I'm going to move that negative 200. It becomes 208 in this sort of what we've classically been calling our B vector. Right? So in here, we had this T0 and this T5. Well, once I move that over, since those are constants, those go away. And so they're not very interesting. So I'm only left with actual variables of T1, 2, 3, and 4. So I can take these equations and turn them into a matrix. Hopefully this is becoming routine and not very confusing, how we can take these equations and turn it into matrix form. Right? And we're left with this matrix down here. What you'll notice is we have a tridiagonal matrix. On the lower left-hand side, we have zeros. The upper right-hand side, we have zeros. And then we have sort of these 3 stripes down the middle. This means I can use my tridiagonal matrix shortcut in solving out my linear equations. So here I've taken that, I've posted that again. I'm going to write out what my equations are. So let's write out a big matrix. And we can automatically fill in the first row, right? That first row should always be a freebie because we're not changing anything in that first row. We're just writing everything out, right? Because that first row doesn't get changed. It's only in the second row where we start seeing change. We know automatically that we want a 0 there because these 2 equations are there to help us get a 0 in that next column of the second row. So we can do for our math f of 2, so we're going to solve for this spot first. F of 2 is the original f of 2, which was 2.04. minus e, so in that same row, so that's minus 1 over f of I minus 1, in this case it's 2.04, times g of I minus 1, that's times negative 1. Right? And that's going to give us what's going to go into that dotted box. In this case, when I do out the math, that ends up being 1.59. So I can put that in here, 1.59. Nothing is going to happen to that negative 1, right? Because there's a 0 there. So I just pull that 1 down. The 0 stays a 0. But I need to account for what's happening at that 0.8. So we need to figure out what's happening in this space right here. So we're going to do the same thing. We're going to use the tridiagonal equation. So R2 for right 2 is going to be the old right 2, 0.8. And all this sort of stuff, so this negative 1, that's E1 over 2.04, that's f of I minus 1, and then times, we multiply that by the R value of that first equation, so that's negative 40.8. When I multiply all this out, we end up getting 20.8. So we can put that number in, 20.8 here. Now we're ready to check and see what's going to happen. Now we're ready to see what's going to happen in the on that next line. I'm going to clear some of this out, just so we're ready to do have some math workspace again, and then I'll probably switch color. So once again, we get a few freebies, right? So now looking at line 3, we have that 0 there. There was a 0 always there. We're specifically working to get a 0 here in that next spot. So we're really looking at what's going to happen here. We get to keep that next negative 1, and then what's going to happen in that outer spot. So let's do this out. So we're going to have F3 is going to be the old F3. Oh, that was 2.04 minus E3, that's negative 1, over Fi minus 1. So in this case, we don't take 2.04, so we don't take that one. We want to use this previous value. So we want to use 1.59. That's the true row above it. Okay, and then we want to take gi minus 1. So what's happening in the row above it? It's still negative 1. So when I multiply all of this out, I'm going to end up with 1.39 in that column. Right, so we're ready to do R of I. So what's the value that's currently there? 0.8. Once again, we don't want to pull this 0.8. I want to pull the entry above it. So when I put this in here, we still have negative 1 and 1.59, but we're going to use for this R minus 1, 20.8. Okay, so because we still keep EI and Fi minus 1, so that's these two numbers, and then Ri minus 1, that's that 20.8. When I punch all those numbers in, we end up with 14.22. That ends up going in that space, and we're ready for the next line. I'm going to do this one a little bit faster. We get all zeros in these spots. I can do my F3 and R3 equations again. We end up getting 1.32 and then 210.99. So you can see in relatively quick fashion, I'm able to fill in this matrix, right? Much faster with this forward elimination, tridiagonal forward elimination, as compared to having to sit there and do all these functions again and again and again, right? So now we're ready for back substitution. Now we're ready for back substitution and solving for and determining what T1, 2, 3, and 4 are. I'm not going to go through that because that's going to look exactly like we saw in sort of that base case Gaussian elimination. But I will show you what the answer is. So if you go in and do that, we can calculate at each of these points, T1, 2, 3, T1, T2, T3, T4, and then we already had T5 and T0. Just as a reference, I put in the analytical solution, and we can see that this numerical approach via algebraic equations gives us quite good answers in comparison to that purely analytical method. With that, that's going to bring to close our coverage of Gaussian elimination and simple matrix equation solving techniques. Hopefully you now feel you're starting to get comfortable with Cramer's rule, forward elimination, back substitution. You can understand the idea of conditioning of some matrices, so making sure that we have that diagonal, which is has a large number at the front, so we don't have these division by small numbers. If we do, we can use partial pivoting in order to make sure that we get large numbers on the diagonal. And then if we have a tridiagonal system, we have a relatively efficient and straightforward way to format our matrix. All right, see you in class.